Today, we're going to pull back the curtain on the mathematics behind a whole class of strategy games. We're going to reveal the secret, the actual mathematical secret that lets you guarantee a win.
So, picture this. You're playing a simple two-player game, maybe taking sticks from a pile. What if I told you there's a way to know, right from the get-go, if you can absolutely force a win? This isn't about being clever, it's not about luck, it's about math. Okay, let's get into it.
The kinds of games we're talking about have a specific name: impartial games. And that word impartial is everything. It just means that the moves available only depend on the state of the game, not on whose turn it is. From the same position, both you and your opponent have the exact same options. That right there is what makes them solvable. So here's our game plan for today. We're going to start with the absolute foundation, winning and losing states. Then we'll jump into the famous game of NIM, uncover the math secret behind it, and then see how that one secret unlocks a universal strategy for pretty much all of these games. And of course, we'll wrap it all up with some key tips to make sure you've got this down cold.
Okay, first things first. To master any of these games, you have to stop seeing a collection of pieces on a board. Instead, you have to learn to see it as a series of states. And every single one of those states is one of two things. It's either winning or it's losing.
So what do we actually mean by that? Well, a winning state is just a position where, if it's your turn, you can make a move that guarantees you'll win no matter what your opponent does. And a losing state is the opposite. No matter what move you make, if your opponent plays perfectly, you are going to lose. The really critical thing to get is that there's no in-between. Every single possible position is one or the other.
Let's make this real with a classic example. Imagine one pile of sticks. You and a friend take turns. On your turn, you can take 1, 2, or 3 sticks. Whoever takes the very last stick wins the game. Simple enough, right? So let's say we start with 10 sticks. Is that a winning position or a losing one? How would we even know?
Well, the way to solve this is to work backwards. Think about it. If there are 0 sticks left, that's a losing position, because the person before you took the last one. Now, what if there are 1, 2, or 3 sticks? Well, you can just take all of them and win. So those are all winning states. But what about 4 sticks? If there are 4 sticks and it's your turn, what can you do? You can take 1, leaving 3. You can take 2, leaving 2, or you can take 3, leaving 1. Notice something? You've just left your opponent in a winning state every single time. That's why 4 is a losing state. And if you keep applying this logic, you see this amazing pattern emerge. As you can see on the chart, any number of sticks that's a multiple of 4 is a losing state.
And that right there is the golden rule. A state is a losing state if every single possible move you can make from it lands your opponent in a winning state. You're basically trapped. So back to our 10 sticks. You can see the pattern. 4, 8, 12 are losing positions. So from 10 sticks, you take 2 sticks. You leave your opponent with 8. Bam! You've just pushed them into a losing state. That is the entire strategy.
Okay, that was a good warm-up. Now let's really up the complexity with the classic game of NIM. Instead of just one heap of sticks, NIM has several heaps. On your turn, you pick one and only one heap and take as many sticks as you want from it. You can take one, or you can take the whole heap, but the goal is the same: be the one to take the last stick.
And this is where it gets really tricky. That simple multiple of 4 trick is out the window. If you're looking at a board with heaps of, say, 10, 12, and 5 sticks, the number of possible moves is just enormous. Trying to map out all the winning and losing states by hand would be an absolute nightmare. We need something more powerful, a much more elegant tool.
And that tool has a fantastic name: the NIM sum. This is the mathematical key that unlocks the entire game of NIM, and as we're about to see, a whole lot more. It might sound intimidating, but the idea behind it is just beautiful.
The NIM sum is calculated using a little binary operation called XOR, which is short for exclusive OR. Now, don't let the name scare you off, it's dead simple. When you XOR 2 bits, the result is 1 only if the bits are different. So 1 and 0 is 1. But if they're the same, like 1 and 1 or 0 and 0, the result is 0. That's it. The magic happens when we do this column by column for the binary versions of our heap sizes.
Okay, let's walk through our example. Heaps of 10, 12, and 5. First, we write them in binary. 10 is 1010, 12 is 1100, and 5 is 0101. Now, we just add up each column, but without carrying over. That's what XOR is. So let's look at the rightmost column. 0 plus 0 plus 1 is 1. The next column over, 1 plus 0 is 1. Next one, 0 plus 1 is 2, which is 0 in XOR. And the leftmost column, 1 plus 1 plus 0, is also 0. So we get 0, 0, 1, 1, which in decimal is the number 3. The NIM sum of this state is 3.
And here it is, the absolute golden rule of NIM. A position is a losing position if and only if its NIM sum is 0. That's it. So, since our NIM sum was 3, the state 10, 12, 5 is a winning state. We know for a fact we can force a win from here. The question is, how?
This slide gives you the playbook, the exact algorithm. Let's do it with our example. Step 1, calculate the NIM sum. Done. It's 3. Step 2, find a target heap. The rule is, you need to find a heap where XORing its size with the NIM sum makes it smaller. Let's check. 10 XOR 3 is 9. Hey, that's smaller, so that's a candidate. 12 XOR 3 is 15. Nope, bigger. 5 XOR 3 is 6. Also bigger. So our target has to be the heap of 10. Step 3, make the move. We reduce that heap of 10 down to the new value we found, which was 9. The new state of the game is 9, 12, 5. And guess what? If you calculate the NIM sum of that state, you'll find it's 0. You just handed your opponent a mathematically guaranteed losing position.
Okay, take a breath, because this is where things go from being a cool trick for one game to being completely mind-blowing. The logic of NIM isn't just for NIM. Thanks to something called the Sprague-Grundy theorem, it applies to all finite impartial games. This is like the grand unification theory for strategy games.
The core idea of this theorem is just stunning. It says that any position in any impartial game you can think of is secretly equivalent to a single heap of sticks in a game of NIM. We just have to figure out how big that imaginary heap is.
And that equivalent size has a name. It's called the Grundy number, or sometimes the NIM value. So how do we find it? We use this nifty little function called MEX, which stands for minimum excluded value. To find the Grundy number for a position, you look at every single move you can make. You figure out the Grundy numbers for all the states you can get to, you put all those numbers in a set, and then you find the smallest whole number that's not in that set. That's your MEX. That's your Grundy number.
Let me give you a really simple example. Let's say you're in some position, and you can make 3 possible moves. And let's say we already figured out that those moves take you to positions with Grundy numbers of 0, 1, and 3. So our set of reachable Grundy numbers is 0, 1, 3. What's the smallest non-negative integer that's missing from that set? Well, 0 is there, 1 is there, 2 is missing. So the Grundy number of your current position is 2. It's strategically identical to a single NIM heap of 2 sticks.
Now, this concept becomes incredibly powerful when you realize that some big, complicated games are actually just a bunch of smaller, independent games being played at the same time. You know, like a game with several different puzzles on the board, and on your turn, you just pick one puzzle to work on. The Sprague-Grundy theorem tells us exactly what to do here. You just treat each of those little subgames like it's a single heap in NIM. The size of that heap is just the Grundy number for that subgame's current state. Then, to figure out if the whole game is winning or losing, you do exactly what you do in NIM. You calculate the NIM sum of all those individual Grundy numbers. If that total NIM sum is 0, it's a losing state. If not, it's a winning state. It lets you break down a massive, complex game into the simple, solved rules of NIM. It's brilliant.
Okay, that was a lot to take in, I know. So let's bring it all home. Let's recap the absolute must-know ideas and give you a clear path to making this strategy your own. All right, here are the big 3 takeaways. First, every single position is either winning or losing. Your job is always to make a move that puts your opponent in a losing position. Second, for NIM, the NIM sum tells you everything. 0 means losing, not 0 means winning. And third, the huge one, the Sprague-Grundy theorem says that any impartial game can be thought of as a game of NIM, because every state has a Grundy number that acts just like a NIM heap. So if you're trying to master this, say for an exam, here's your 3-step plan. 1, get that winning/losing logic burned into your brain. Play out those simple stick games. 2, practice your NIM sum calculations. Get so comfortable with binary and XOR that you can just do it without thinking. And 3, get your hands dirty calculating Grundy numbers. The MEX function is easy once you've done it a few times, so just work through some examples.
So there you have it, the mathematical blueprint for winning. It's this incredibly powerful way of thinking that turns games that seem chaotic into puzzles that are completely solvable, which kind of leaves us with one final thought, right? Now that you know this secret, now that you can see the hidden structure in these games, where else is it hiding? What other complex situations in the world might just be an impartial game, waiting for someone to come along and solve it?